So we were at this point where we were discussing the traversal of the graph, and we started off with the depth first traversal, where we said that the visit of the nodes will be uh, across the depth, and once the full depth is discovered, you get back and start discovering another branch of the graph. So, and we also uh, were looking at an example. So let us redraw the example. So one possible visit sequence could be as follows. So let's say that we start from the node 1. We start our visiting from the node 1. Let me do it a little bit more cleanly. So this is a possible visit sequence if you follow the recursive algorithm that we had written. And we already said that a DFS can be simulated using a stack. In this case, we were using recursion or recursive calls to implement the stack. Now, we will define something called a DFS tree. So what is a DFS tree? While executing DFS, if DFS visit U calls DFS visit V directly, then we connect UV by what we call a tree edge. We connect UV by a tree edge and name V a child of U. So U is an ancestor of V and V is a child. They call it parent. And V is a child of U. So that's how the relationship is typically expressed. Okay. Now, any DFS will have two important orders. Can you guess what are these two important orders? Any thoughts on this?
The order in which the nodes are visited.
So that's one order. Why am I saying two orders?
So depth wise and breadth wise.
No.
Sir, another order of when the nodes are completely explored.
Very good. So basically in terms of stack, can you elaborate
Sir,
a little bit in
when
terms
a
of
node
this?
is popped and when a node is pushed.
Excellent. Very, very good. This is something that you should remember. So when a node is pushed, okay, if you are looking at this order, then this is called the pre-order of the DFS. And when a node is popped, if you are looking at this, then this is called the post order of the DFS. Now quickly tell me the pre-order and the post-order of the visit sequence. Somebody is on unmute. So quickly tell me the pre-order and the post-order of the visit sequence tree that I have just now drawn for that graph. For this one.
Sir,
Huh?
1, 2, 5, 7.
1, 2, 3, 4, 5, 6, sorry, 6, 7. Right? What is the post?
Sir, 3,
3, 4,
3,
2,
4, 2,
7,
7,
6,
6,
5, 1.
5, and 1. These two orders come very handy. We will see soon why.
Sir,
Yes.
sir, here 2 is visited twice, right? From
2
1 to
is
2, visited twice. Because when we
visited twice. No node is visited twice.
start with 1 and go to 2, right?
Yes.
And from 2 we go to 3.
Yes.
Then we come back by popping 3. That means
Yes.
aren't we visiting the 2
No,
second
we are
time?
not visiting. The visiting mark is done. So we are only coming back to 2 to go to 4. You have already marked 2 as visited and you are recursively calling the function to visit all the neighbors of 2 one by one.
Okay.
Okay, so by now, I guess you have already understood that a DFS tree is non-unique. Okay. So a very simple example. I mean, you could have done it with the previous example also. I'm drawing a smaller one so that I can do it quickly. So for this one, you can have one DFS tree like this, another DFS tree like this. Okay. So many such DFS trees are possible given a graph. Okay. So now tell me, would it be easy to guess what is the graph structure if you are given a DFS tree? Will you be able to easily guess? Suppose I give you this graph structure. Suppose I give you this graph structure, will you be able to?
No, sir.
No, sir, there are many possibilities.
Yeah.
And we don't know if some edges are connected or not.
Yes. So given a given a DFS tree, it is very difficult to identify the or map back the original graph structure. Okay? Because it's non-unique, and therefore you can have many different ways of reconstructing the graph. Okay? And we have already seen that the running time is order m plus n because you are visiting every node as well as every edge.
Sir, I didn't get this. If we are visiting a node, we are passing through edge. Do we need to again add edge?
You are counting all the edges also. Look at your algorithm. For each vertex u, if u is visited, if u visited is false, then DFS visit you. So you are going by each vertex and then you are exploring all the edges of that vertex. Okay. So you see, you are going here from 1, you are exploring this edge. So you are visiting this node, then you are exploring this edge, you are visiting this node, you are then going back, exploring this edge, visiting this node, going back, again going back, again going here, visiting this node, exploring this edge, again from here, visiting this node, exploring this edge, then from here, visiting this node, exploring this edge, and then you get back. I mean, just the unfolding of the recursion stack. So therefore, you have to,
How can we differentiate visiting the node and exploring the edge? I did not get that.
visiting a node. So when you are at a node, you mark it as visited. Okay, that's what you are doing. Look at this one.
Yes, sir.
Whenever you are at a node, you are marking the node as visited. And then what you are telling, for every outgoing edge, there is a for loop going on here. For every outgoing edge, you comma v. So for every edge, you have to call this DFS visit. Is this getting clear now?
Yes, sir.
So that's what is very, so it's like, it's very important to look at the algorithmic fragment. Okay, so here is where each edge is coming, and here is where each node is coming.
Sir,
Go ahead.
sir, like sometimes we are not visiting every edge, but still we are like wasting
No,
time
you
on
have to
checking.
visit every edge.
Sir, but then like sometimes we have already like the visited comes true for it because maybe it's connected to two of the nodes. Like in the
Yes.
before case 4 was connected to 2 as well as 1, so it was already visited when we went to 2.
Yes, true.
So
So
like we are not visiting every edge, right? The 1 4 edge is not visited.
you are not visiting any edge. You are exploring an edge, you are visiting nodes.
Yes, sir. Okay, got it.
Sir, if we are given a DFS tree, then we cannot get back the graph. But if we
No,
are given all the DFS trees, then we can get the graph.
think about it. Think about it if you can get it or not. Good problem to ponder over. If all the DFS trees are given to you, whether you can reconstruct the graph easily. Easily means it should be a polynomial time algorithm. In N and M. It should be polynomial in N and M. Okay. So now the first application. So the edges of the graph after the DFS has been done can be classified into different types. Okay. So first thing to note here is that I guess you have already noted it, that not all edges are part of the DFS tree, right? So not all edges of the graph are part of the DFS tree, right? So those that are part of the DFS tree, edges that are part of the DFS tree are called tree edges. Okay. A forward edge is a non-tree edge from a vertex to one of its descendants. We will soon see this through an example. A cross edge is an edge from a vertex U to a vertex V such that the subtrees rooted subtrees rooted at U and V are distinct. A back edge is an edge from a vertex to one of its ancestors.
Sir, can you please scroll up? Okay, sir.
So let's say this is a graph. Okay. So post DFS, so you are starting from the node S. This is the start. Okay. You start from node S and you start visiting the different nodes in the graph. This is a directed graph. Okay. So in this case, this could be one of the DFS trees, right? A possible visit sequence can result in a DFS tree like this. So here, by definition, so let's start with the easiest one. What is the back edge?
S2A.
These are S2,
B2S.
B2S, yes. So all these back edge, forward edge, cross edge are non-tree edges. These are tree edges. All these are these that we have drawn, and I am ticking. These are all tree edges because they are part of the DFS tree. The back edge here is the edge from B to S, which is there in the original graph, but in the DFS tree, it is absent. Okay. And here, as per the DFS tree, this node is a descendant of this node, and therefore an edge existing between a descendant and an ancestor is a back edge by definition.
Sir,
Yes.
sir, here the direction also matter. Like
Direct.
If S2B is an edge, so we can't say it as a back edge.
No, no,
Okay,
no, no. Only if B2S is a directed edge, then only we can say it's a back edge. Otherwise, no. Okay.
So in case of reciprocals, it's a kind of a back edge. Like one is the
Yes.
back edge.
Yes. Now, what about this edge?
A forward edge.
Yes.
Forward edge.
This was the forward edge. This is the forward edge. Okay. And what about the last one?
Cross edge.
This is the cross edge. So now, just now somebody said that if there was an edge between S and B rather than between B and S, okay? So then what would that edge be?
Forward.
Forward edge.
That would be another forward edge. Now, algorithm to classify the edges post DFS.
Sir,
Go ahead.
sir, is back edge necessarily a non-tree edge?
Yes.
Okay, sir.
Sir,
See,
can you please
See,
explain
this
the
is a very intriguing question. Is back edge necessarily a non-tree edge? If the back edge is present, will the tree remain a tree any longer?
No, sir.
It will have a cycle. And what is the definition of a tree? It has to be cycle free, right? So back edge cannot be mandatorily part of the tree. Somebody else had some other question?
Sir, can you please explain cross edge?
Yeah, so cross edge as it is defined. So it has to be the two nodes U and V should be part of two different subtrees. Okay, the subtrees rooted at them should not overlap, which is what is happening for C and D. The subtrees rooted at them are not non-overlapping. Okay, and therefore it's a cross edge.
Sir, sir, suppose there is a connection between B and E in the original tree.
There is a connection between
B and E.
B and E.
B and E. Yes, sir.
There is no E here.
Sir, that middle. Okay, C. Sorry, sir. It is B and C.
Huh?
Suppose there is a connection between B and C. So, sir, in the DFS tree, what would that connection be called?
So it will not be a part of tree. First of all, you have to find out whether it's a part of the tree or not. Okay.
Sir, it is not part of tree. Yes.
It's not part of the tree. And then, like, your question is like what age it should be.
Yes.
So depends on like which direction it is.
Sir, it is from B to C.
If it is from B to C, okay, let us draw it. Disturbing the original graph. If there is an edge like this, right?
Yes, sir.
That's what is your question?
Yes, sir.
Yeah, so what age would it be?
In
Forward
the
edge.
DFS.
What age would it be? It will be a
Cross
simply
edge.
forward edge.
Cross edge.
Forward.
Why? Why cross edge?
So B and C are children of A.
A back edge.
No, it will not be a back edge.
Sir,
It is not a back edge.
It's a descendant of B, and there is non-tree edge, so forward edge.
It's a forward edge.
So C is not
B,
descendant of
B
C,
is
right?
B is a, so here, like, so depends on how you call it. So if you are from B, if you are calling C, okay. So depends on how you are calling it. So if it is, since it's a depth by depth search, So from A, he will go to B, and from B, he will call C. Okay. In that case, actually this edge will become a part of the tree edge. Depends on how you are calling it. Since you are visiting depth by depth, so as soon as you go to A, and from there, if you are at B, then he will call, from B, he will call C. And it will become a part of the tree edge.
But sir, there is no directed edge between B and C in the structure of tree. Yeah, on the basis of calling, we can say that it is a forward, but by the
No.
structure.
Depends on how you are calling. So if you have an edge like this from B to C, then, and you are at A and you go to B. So B is visited. Now from B, you are seeing that there is one neighbor C, which is still unvisited. So you go to C and then you visit C, and then this edge becomes part of the tree edge. In that case, the edge A to C will not be part of the tree edge.
Sir, if we first visit C, then there will be no connection between B and C. Right?
Yeah, if you first visit C, then you will go back. So from C, you have no other place to go. Then you will go to A, and then you will come to B, and then from B, you will, okay, there is no other place to go. So then in this case, it will be a forward edge.
Sir, why will it be forward? It is cross. It is similar to the relation between C and D.
Okay, let's see. So C becomes, so A becomes an ancestor of C, and A becomes an ancestor of D, and sorry, A becomes an ancestor of B also. So these two are descendants, and we cannot say for sure that B is a descendant of B is a descendant of C. Yes, in this, and also like the subtrees do not overlap. Yes, you are correct. So in this case, these two, if this edge is there, these two will be, this edge will be cross edge. If this edge is there, then this will be a cross edge. Agreed. This will be a cross edge.
So all of these definitions depend on where we are starting, right?
That it depends on where you are starting and which DFS tree you arrive at. See, for instance, as I said, like this DFS tree will have separate back edge, cross edge, and forward edge. This DFS tree will have separate back edge, forward edge, and cross edge.
So once can you explain what is non-overlapping edges?
Huh?
What
Not
is
non-overlapping edge, non-overlapping subtrees.
Yes, sir. Non-overlapping subtree.
So look at the subtree rooted at C. Okay. So at C, you do not have any descendant. So its subtree is null. Okay. And at D also, you do not have any descendant, but their descendants also do not overlap. Okay. So therefore, this is a cross edge. Their descendants are distinct. Even if it is null, they are distinct. And therefore, this is a cross edge. Similarly,
that
here.
means the definition of the cross edge, forward edge, and back edge depends on the tree, the DFS tree. It varies with the.
Of course.
Okay.
It definitely depends on the tree. So that's why I am telling, like whenever, as I said, that algorithm, whenever you will write an algorithm to classify the edges of, this will be always post DFS. That means the DFS is done, DFS is over, and the tree is ready.
Sir?
Only then you can comment on the other types of edges. Yes.
Sir, these definitions of edges, they are all for directed or for both directed
For
and
both.
and sir, is a cross edge necessarily a non-tree edge or is means that
It's
is
always a non-tree edge. All of these are non-tree edges.
So can we say that back and forward edge are also cross edge?
No. How? In some cases it may be, in some cases it may not be. They might have overlapping neighbors. You are fixing yourself to this particular example.
Okay, sir.
Sir, you said that if there is a path with, there is a edge between S to B, directed from S to B, then you said there will be a cycle. Hello, sir.
From B
Sir?
to S, not S to B, from B to S.
Okay. And if it is a part of the tree, then it will become
Yes.
cycle.
If it is a part of the tree, then it will become a cycle. So back edge can never be a part of the tree. And in this way, you have also resolved another application. You yourself with your question and one of your friends have also asked the same question. With this, you have already resolved an application. Do you understand? If you find a back edge while you doing a DFS traversal, if you find a back edge in your DFS tree, okay, then there must be a cycle present in the graph. So this is an algorithm for detecting the presence of a cycle in a graph. We'll come to that in a moment. But before that, what is the prescription to classify the edges? So can you relate the tree edges, back edges, cross edges with the pre-order and the post-order notions that we have just now come across? What will happen for a tree edge or a forward edge? What will be the relationship between the pre-order numbering of U and the pre-order numbering of V?
Pre-order of V should be greater than the pre-order of U.
So you want to say pre-order of U is less than pre-order of V. Anything
As well
else?
as post-order of U should be greater than post-order of V.
Post-order of V should be less than post-order of U. For back edge,
Pre of U greater than pre of V.
pre of V less than pre of U, comma, post of U less than post of V. What about cross edge? This is the only way to determine the cross edge. So this full thing must have happened before this full thing. Okay? Or must have happened after this full thing.
Sir,
Any one of the two.
sir,
Uh,
sir, I'm getting confused in U and V that you have written.
U and V are nodes, and UV is an edge.
Sir, I mean the way that you have written things.
Huh?
Sir, in some places you have written V first and then U second, and it's difficult.
Why have I written so? Why have I written so?
Sir, he means that he's not able to differentiate the letters U and V.
Yes.
Yeah, so U is the, you have to tell me. U is the parent and V is the child.
Sir, can you dictate it once?
Huh?
Sir, he meant in terms of the handwriting, he's not able to
Handwriting,
differentiate.
Oh, okay, okay, oh, okay, okay. Sorry. Okay, so pre-order. Okay. So in the first one, pre-order. I'm very sorry. Let me erase and write it. Let me do it with a different color. Pre-order of U. Pre-order of V. Post order of V. Post order of U. Pre-order of V. Pre-order of U. Post order of U. Post order of V. Pre-order of V. Post order of V. Pre-order of U. Post order of U. Legible?
Yes, sir.
Sir, I didn't get how we are saying the pre-order of U is always less than pre-order of V for forward edge.
For forward edge.
Yes, sir.
Forward edge and tree edge are similar relationships. Only those that are already part of the tree are not part of the forward edge.
Sir, so basically this order.
So this is an ancestor descendant relationship. For tree edge, it is just parent child, and for forward edge, it's ancestor descendant. So tree, it is immediate parent and child. That's why I said that the DFS visit U should directly call the DFS visit V. And here it is ancestor descendant.
So for a parent vertex, we see its order, right? In the graph.
For a parent?
Vertex, U.
Yes, yes.
We see its order.
Yes, everybody's order. We ordered the vertices according to their pre-order and post-order. That is the time at which they are pushed and the time at which they are popped. Based on that.
Sir, could you please explain the pre-order and post-order relation of the for the cross edge? Why the pre-order and post-order are less than the pre-order and post-order?
So for any node, pre-order of V should be less than post order of V, right?
Yes, sir.
Yes, sir. Yes.
You cannot pop without pushing. Similarly here, now I am telling that since they are parts of two, so they are parts, they are two different parts in the graph and their subtrees do not overlap. So that means either this part has been done and then this part has been done, or the other way around. This part has been completed and then this part has been completed. They cannot be interleaved like in the previous two. So either pre and post of this has been finished and then you go somewhere else and its pre and post is finished, or the other way around. This pre and post is finished and then you come and do pre and post of this. So you cannot have an interleaving because their subtrees do not overlap. So there is a strict time ordering. Either it is less than or it could be greater than. This is what I wanted to mean.
Sir,
Yes.
the ancestor and descendant for a tree is like descendant is present in the subtree of ancestor, right?
Yes, yes.
Okay.
That is, some of its DFS visit has called the next node. So basically, like DFS visit of U has called DFS visit of V, and DFS visit of V has called DFS visit of W. Then W is a descendant of U.
Okay, sir.
So this you will try. If you cannot, let me know. I'll share the proof. But you should try. And this is if and only if. So both sides need to be proved. That is, if G forward side, if G has a cycle, then there must be a backage. If backage is there, then G must have a cycle. So you have to prove both sides. Try this. Let me know on this team chat whether you are able to do it. If not, I'll show you.
Sir, can you scroll a bit up? Okay, sir.
So assuming that this is true, So let us assume that, so this is a theorem, and assuming that this theorem is true, can we write an algorithm to find the cycle, like to find whether a graph has a cycle or not? So this is also called the algorithm for cycle detection. So for this, we will use a simple DFS with some small modifications. A simple DFS should be able to do, because we have to just find out whether a back edge is present or not. Okay, so we will do some very simple modifications in the DFS algorithm that we have learned, and that should be enough to find whether there is a cycle. We will denote colors for the different types of nodes. So with these three different colors for the nodes, we are now ready to write a very simple and quick algorithm for cycle detection. Color every node V in V as white.
Sir, can you please scroll up?
Are you telling something?
Sir, can you please scroll up?
Done?
Yes, sir.
So again, very similar to the DFS basic pseudocode. If color of V is equal to white, then do DFSV. Set the color of V to gray. So that is, exploration has started for V. For all nodes W adjacent to V, do if color of W is equal to gray, what has happened?
We have explored its parent.
That means
Means we do not need to call for DFS visit of W.
that's true, but what does
Sir, it will
this
be a
mean?
cycle because both are
Very good.
currently in searching.
Spit out cycle found. Else, if color of W is white, then DFS W. Finally, coming out of the loop, color of V is set to black. So you have just simply modified the DFS algorithm, the basic DFS algorithm, but now as soon as you have discovered a back edge, you flag that a cycle is present. If you are never able to discover a back edge in your whole DFS traversal, then that means that graph does not have a cycle. Okay. So now I'll give you a small teaser. Orijit, are you already in the meeting? Any speciality of this graph that you can note?
It's a DAG.
It's a DAG. Very good. So for others, it's a directed graph. It's also an acyclic graph. So together, it's a DAG. And we had discussed about this special type of graph earlier. Now, any DAG can be topologically sorted. So this is another application of DFS.
Sir? Sir, but it has a cycle, right?
Where?
Sir,
Where do you see a cycle?
I think he meant 154.
Huh?
I think he meant 1 to 5, 5 to 4, 4 to 1.
No, but that is not like that. So the age from 4 to 5 is reversed. If the age was from 5 to 4, then it would be a cycle. Can't hear you. There is a lot of noise.
Sir, I have a doubt regarding the above algorithm for finding the package.
Huh?
Yes, sir. If there is an adjacent node which is also gray, that means that is also exploring its edge. Then how can we say that there must be a package? Because it doesn't mean that there will be a edge which comes back to the source node.
No, I'm not able to get you. Which one? Which algorithm are you asking? This one, the
Yes, sir.
cycle detection.
Yes, sir. Yes, sir.
Yeah. So what is the question?
Sir, here we are using a for loop there for finding all the adjacent nodes of the V. So we are saying that if the color of the W is gray, then there will be a cycle found. But sir, how can
Yes.
we say that there is a adjacent node which is also exploring its edge? So that will be must be a back edge.
No, that is what we are checking. We are checking that whether the color of one of the adjacent nodes of W is gray. That means it has already been visited. And you are trying to visit it again. In the course of the DFS, it has already been visited from some other path. So a graph can have multiple paths through which W can be reached, right?
Yes, sir. But at that time, if so, how can we say that there will be must be a cycle? That if we have reached that node by another path, so there may be the many paths to reach a node, but
I can't
yes,
hear
can't.
you at all. I can't hear you at all. Your voice is breaking.
He's
Hello,
asking
now
why
am I
it
audible?
should be a cycle should be found if there is another node which is gray.
There is another node which is gray. So that means, so what are we telling? That V has a node. V has a node W in its adjacency, which is gray. That means W is also an ancestor of V. You started with an assumption that V is an ancestor of W. Now you are seeing that W also is a potential ancestor of V because it's already gray.
Yes, sir.
Are you getting me?
Yes, sir.
And therefore there is a back edge.
Yes, sir.
But sir, for undirected graph, this algorithm will always give cycle found.
No. Why?
Because sir,
Which algorithm?
Undirected graph, the cycle detection.
Say this is an undirected graph.
Yes, sir. So from the start,
Where is the back edge?
But sir, I'm talking about the algorithm, sir, because each edge has a means all edges are bidirectional. So if we check for a node, we will also check for its parent. Then parent will always be gray, but that does not mean that it has a cycle.
No, we will not check. Where are we checking for its parent?
Because we are checking for all edges, all nodes adjacent to you.
Yes.
So
and we are checking if the for all edges W adjacent to V, if the color of W is gray, that's what we are checking.
So sir, suppose we have two nodes in the graph connected by an edge. So
yes,
let us number them 1 and 2. Now we first call on 1 and we color it as gray. And now the node 2 is adjacent to 1, right? So its color is white. So we call for 2 and we color it as gray. Now we check for nodes adjacent to 2. So the node adjacent to 2.
No, there is no other adjacent node to 2 for which we need to do a DFS. Its color will become black immediately after it comes out of this loop.
Sir, I am talking about an undirected graph. So adjacency list will store u comma v and v comma u both.
True. So what?
So when we check for 2,
the same path from 1 to 2 and then 2 to 1.
No, I'm not getting you. Suppose this is marked as, so suppose you are telling that you have a graph like this, right? As simple as this.
Yes, sir.
Fine. So now you start your DFS. So you have this as white, this as also white. Now you turn this to gray.
Yes, sir. Now we will seek for its
now you will see
neighbor.
for its. Now you will see for its neighbor. This is white.
Yes, sir.
Yes, sir.
Okay. So this is white. You will call DFS.
It will become gray.
It will become gray. Okay.
Yes, sir.
It will
Now
become
again,
gray.
when we will search for its neighbors, W will come again.
No,
W would already have been black, no sir, by then.
W. So at this point, what will happen? W has already become black because W has no other neighbors left.
Sir,
So you have
give,
called W.
sir, give
You
another
have called
child to W.
DFS.
We are
Sir,
writing
give
the
one more
color
child to
black.
W, then it won't happen.
No, every time that child will become black.
Sir, but the adjacency list will contain of 2 will contain 1 also, no?
So what?
So we will go to 1.
Sir, we are calling the DFS before making it black.
You are always calling a DFS. This is a recursive call.
Sir, if you give one more child to W, then
that child will become black.
No, sir.
Because its DFS has ended.
Sir?
Sir, without visiting all the neighbors, how will we know whether or not it is white?
I don't understand what you are telling.
Sir, if we
We
name
are
them,
calling TFS only if it is white. So, sir, if W
No,
has one more child, then
if all of you are talking, then it is very difficult to answer.
So can you go line by line from the code?
Yes.
Yes, sir. So
initially,
we will make the
there
first
is-
one gray.
yeah, no, you have DFSV. You come here, you make the first one gray. Okay.
Yes.
Now you look at its neighbor. Okay. So its neighbor is white,
Yes, sir.
right? Its neighbor is white. You call DFS.
Yes,
You
sir.
make it gray. Okay.
Yes. But the other
Now-
one is still gray, not black.
its parent.
Who
sir.
is?
If we
Yeah,
name
its
it,
its parent is black.
No, sir. It is still gray.
Yes, sir.
We have not made it black yet.
No, it's still gray. Yes, it's
Yes.
still gray.
Yes,
So
sir.
now for all nodes, W adjacent to V. Okay, so now
Sir, shouldn't there be an extra condition that W is not a parent of V?
Yes, sir. It should be written explicitly.
wait. W is adjacent to V.
also, sir, if we mention that it is not
It will
immediate,
become an infinite loop.
And V is not already gray. This should work.
Sir, in that case, it will not find any cycles.
Yes, sir. If we say it's
Here,
Sir,
we
it
gray
will
in
not
the
detect
immediate
gray
previous
at all.
line.
Sir, we need to mention that it is not immediate parent.
then
No,
it
no,
will
no.
be for parallel edges.
No.
So the same algorithm wouldn't work for the directed and undirected. We will have to change for undirected.
So we have to make another parameter called parent.
Yeah, for the undirected graph, you have to change this a little bit. Yeah, so this will work for the directed graph because so there is a explicit adjacency, and so therefore this will work for the directed graph. And we will be doing the directed cycle. So we have to make some small modifications here and there for the undirected graph. I'm sending this just after the class, the undirected graph algorithm. So let's finish this, because otherwise you will not be able to follow the tutorial. Let's finish this and then I'll be sending you the implementation of the pseudocode for the undirected graph. That's also not very difficult. Okay, so as I was telling, that a DAG could be topologically sorted. Okay, so what does that mean? So topological sort is a ordering of the vertices such that edges go from predecessor to successor vertices. Okay. So again, this is, as you can always understand, this is only effective for a DAG. A topological sort can only be done on a DAG. Okay. So what do we mean by predecessor and successor? Here U is the predecessor and V is the successor. Now, how do we produce the sorting of a DAG? Any idea? Okay, let me give you some example of the topological sorting of this particular graph. So what could be some of the topological sortings? It could be 1, 2, 3, 4, 5, 6. This is 1. It could be also 1, 4, 2, 5, 3, 6. There could be many others.
Sir, on what basis is the second one sorted?
Huh?
On what basis is the second one sorted? 1, 4, 2, 5, 3, 6.
Think.
It is from
Predecessor will be before the successor.
So the predecessor has to be always before the successor.
Yes, sir, but how 2, 4 and 2 are related?
One, okay, then 4. Yes, this is also correct. This is also correct. I claim that this is also correct. There may not be any relation.
Sir, we will check by the outgoing degree.
That's the greedy approach. That's a correct approach, but that's a greedy approach. But how do you do it using DFS? Orijit, are you here already?
Sir, we sort it according to the post order of the DFS in decreasing order.
Exactly. So what you do is you sort it according to the post order of the vertices. That's enough?
Sir, and reverse it.
Yes. So this is the topological sort. So using DFS, you can compute the topological sort by just arranging the vertices in post order and then reversing the order. Okay, this gives you the topological sort and the ancestor descendant relationship that you want to maintain. So basically, the ancestor, the predecessor successor, or the ancestor descendant relation we will be using these terms interchangeably all through. As long as I am not telling that it is a parent child, you have no reason to assume. So somebody said, what is the relationship between 2 and 4? You have no reason to assume that they are direct parent child, unless and until I have explicitly mentioned that these are parent child relationships. I said it's predecessor successor, or it could be ancestor descendant. So now,
Sir, can we traverse this whole graph as a tree?
traverse this whole graph. Why not?
Yes.
Why not?
Sir, how can we go to 2 from 5? I mean, it is directed from 2 to 5, but we cannot go from 5.
Can you go back to the DFS algorithm? The basic
Yes.
algorithm, and look at the first part of the algorithm. What is it telling? Not DFS visit, DFS.
So if it is visited, then we go through its outgoing edge.
That's what you do. So 2 is visited. Is 2 visited?
No.
So then you have to do the visit for 2, and then that. So basically you have, so it's not that after the traversal, after the DFS traversal, you will always get a single tree. You might get a forest of trees, because the graph might be disconnected. It's not only in this particular case. The graph might also be disconnected. So what will you do? You will traverse a part of it and not traverse the rest? That's not what we will do, right?
Yes, sir. We will check all unvisited vertices and.
Yeah, so basically that is why it is said for each vertex.
Am I audible?
This has to be done for each vertex. So 2 will remain unvisited, and therefore, since it is false, it will start with 2 again. This is a different chain. Then the same thing will happen with 3 also in that graph.
Sir?
Yes.
Sir, in case of a DFS, we are given a start vertex. So for topological sort, do we need a start vertex, or we can compute even without a start vertex?
You just run a DFS.
Means okay.
You just run a DFS. Find the
So,
post order and reverse that post order.
Okay, sir.
Because you are sure that post order will tell you the ancestor descendant relationship. And if you reverse the post order, then it will give you the ordering from ancestor to descendant. As simple as that.
Okay, sir. Understood.
The other way, somebody has already mentioned, the other way to do topological sorting is a greedy approach. So what you do there is you start with any vertex that has an in degree 0.
And sir, am I audible?
Yes, you are.
Okay, sir.
Orijit, is it Orijit?
Yes, sir. Actually, I have tried many times. I think
Yeah, I
in
have.
computer there is some issue with the sound. That's why I'm logging.
Okay, so I have been calling you for a long time.
Yes, sir. Actually, I sent message in the meet also.
Okay, I did not see it. I was taking the class. So I'll finish in another 5 minutes and then you can take up.
Okay, sir. Thank you.
Okay, so somebody already suggested this algorithm, and this is also a greedy approach to find the topological sort. So what you do is you identify nodes that have 0 in degree. There are 3 such nodes in this graph. Okay, start with any one. Okay, say 1. Remove the 2, remove the nodes and the edges associated with 1. What is left? This is also a very fast way of computing the topological sort. Then, how many nodes are there with in degree 0? 3 nodes, right?
Yes, sir.
4, 2, 3. Remove any one. Okay, so your order becomes 1, 2. Now then remove this one. 3. Remove this one. 4. Remove this one. 5 and then 6. Okay, so this is a greedy approach to achieve the same thing. So we will close this chapter with the other form of traversal where we are doing a breadth by breadth. Traversal. Just like we have been doing all this time for DFS, we have been doing depth by depth. Okay, you go depth wise and then you come back and then you come back and then you come back and do the traversal. Here you do the opposite. You visit all the breadth. Okay, then you go to the next breadth, you visit those, then you go to the next breadth and then you visit those and then you finish. Okay, so this is the other way of traversing the graph, and this is called the breadth first traversal. How will you implement this? Which data structure will you use?
Q.
Q. For every node U in the vertex set, we do BFS visit mark U visited. Add U to Q. Let's call the Q Q. While Q is not empty, let's set V as the head of the queue. For W such that VW is an edge, do if W is not visited, do what should we do?
Push in the queue.
You don't push in the queue.
In queue.
BFS visitor.
If W is not visited, then mark, first you have to mark W visited. Then add W to the queue. Once all the neighbors of V has been done and enqueued into the queue, remove V from queue. It's a simple correlate of the DFS. Just another way of traversing the graph. So it is traversing breadth by breadth, or sometimes also called the level by level traversal. Okay. So we'll stop here, and now Arijit will show you the previous year experiment that we gave in the lab, and this will be also a nice example for BFS. Okay, an application and a nice example of BFS. I think he's going to show you both the BFS and DFS applications, but like this is anyway, so I'm not giving an example for BFS like the one that I gave for DFS, because Arijit is going to give you an example now through the last year's lab experiment. So we will stop here, and I'll give the stage to Arijit. But before I leave, I'll have to send you the cycle detection for the modification in the cycle detection for the undetected graphs. So that we will do. So while Arijit starts up, I'll write the code and send it. I mean, write the pseudocode and send it over chat. Any questions? Okay, Arijit, you can start off.
Okay, sir. Thank you. So I guess now I'm audible.
Yes, you are.
Okay, so I'm just sharing my screen.
Yeah, let me stop sharing my screen. Otherwise, you'll not be able to share. And I think I'll have to make you a presenter. Otherwise, you will not be able to present. Okay, for the time being, I am making everyone the presenter so that you can also present. And it's already getting recorded.
Okay.
Yeah, Orijit, you can start. You can share your
Okay.
screen.
Hello. Hello, am I audible? Hello.
Yes, sir, you're audible.
Yes.
Okay.
Yes, sir.
Okay.
Yes,
Thank
sir.
you. Okay. Just wait for a minute. But I cannot share my screen.
So, Orijit, there is an arrow icon, you see? The third button. Are you using a laptop?
Yes, sir. I'm using the laptop, but I can.
Yeah, so there will be a rectangle and an arrow inside it.
Just beside the leave button.
Can you see it?
Okay, okay, sir. Share content. Yeah. Yes, sir. Yes, sir. Yes. So I think now it is visible. My screen is visible. Yeah. Okay, so let's start. So basically, this is the agenda. So first we will discuss the graph traversal related lab assignment, and then we will discuss briefly about what is strongly connected components. After that, if time permits, we will go for some applications for topological shock. So okay, so let's start. So this is the previous year. So this is the previous year's question. So basically, the question is long. So basically, I don't think while reading this it will make any sense. So I will just go to the picture and tell you what is the question. So basically, if you can see the grid, and there are some red tiles, and there are some one is green tile and one is orange tile. So basically, what is this tiles represent? So each of these tiles you can think of a stone. Okay. So basically, now here is the 0, 0, 0, 1 is these are all the coordinates. So the question said that the frog named James sitting on this orange stone with the coordinate 0, 2, and he want to eat a fly or some insects which is sitting on this green tile with the coordinate 5, 5, 4. Okay. Now now there are some catch. So basically the fog can move in any direction. So in the north, south, east, or west with just one just one step. So basically from 0.02 he can move to 0.1 or 0.3 or 1.2. So basically he can move just one step. Now the point is that like there are some red tiles also. So basically red tiles are the unstable.
I muted.
Sir, you're muted.
Okay, sorry. So is it fine?
Yes.
Okay, sorry actually. So basically I'm again started with the agenda. So basically the agenda is that I will discuss about the graph traversal related lab questions of the last
No,
year.
Orijit, this was covered. You can go. So I think we just missed you at that red tiles.
Okay. So basically that's what I'm saying. So basically the red tiles are the unstable stone. So basically the frog need to avoid these kinds of stone to reach its final destination, that is the insect. Now you need to tell. So you have been given all this information, the tile and the positions of the frog and the positions of the insect and all the unstable tiles location. You need to tell is there a path to go from his location to the insect's location. So that is the question. So these questions can be handled by two ways. So basically, you can do it by DFS and you can do it by BFS. So basically, the questions has two parts. In the BFS implementation, you don't need to tell the path. So basically, there is a path you can see from 0 to 0, 1. Then you can go through all these things and you can reach to 5, 4. But in the part that asks to implement it with BFS, don't tell you to track the path. So you just need to say that yes, the path exists. That's all. You don't need to print the path. Okay, but the DFS implementation, you need to also print the path. So from the frog to the target. So that is the question. Now we'll start with the BFS part, and after that we'll do the DFS. Okay. So the question is clear to all, is it? Hello.
Yes, sir, it's clear.
Okay. So I'm just going to the next slide. Okay. So we'll start the BFS. So yeah, as the sir, I think just a few minutes earlier. So talking about the BFS. So BFS will use the queue. Okay. And here our starting vertex is the 0, 2 because we want to start from our current location for which is 0, 2. So we will insert 0, 2 in a queue. Okay. So we'll insert the 0, 2 in a queue. And then after that, what we'll do, we'll now dequeue that the front element from the queue, which is 0, 2, and we will move its adjacent node in the queue. But we need to remember, we will not like for 0, 2, there are 3 adjacent nodes. So which is 0, 1, 1, 2, and 0, 3. But we will not include 1, 2 in the queue because we know that we cannot go to 1, 2 because it is an unstable node. So we need to avoid this term. So what will be the next step? Next step will be, so yeah, this is the next step. We will dequeue the 0, 2 from the queue and we will add its reachable neighbor into the queue. So basically this will be the setup. So we will dequeue 0, 2 and we will enqueue 0, 1 and 0, 3 into the queue. So I'm just marked the fast node as orange just to like represent it is the front element of the queue because we need to remove the front element each time. So that is just to take care of this thing. So there is nothing other than that. So there is no color coding and all these things. I'm just doing it to understand that this is the first element of the queue. Okay. Okay. Another thing we need to do while after the adding those the node into the queue, we need to color those nodes. So to understand that these nodes are already exposed. So like we will not go through those node again. So basically the diagram will become this. So we'll mark this 0, 1 and 0, 2 with the green color, representing that these two are already explored. So explored means that we'll somehow encode enqueue those two tiles into the. So okay, again, what will be the next step? Again, we will enqueue.
You're muted
Sir,
again.
you're muted, sir. Sir, you are muted.
Yeah. Why it is happening? I think someone is doing mute.
Yes, sir. Someone is also removing our students from the meeting, sir. Is it
Yes,
possible?
sir.
Yes,
Yeah,
sir.
so
Ah,
this is
Difficult for
I
me.
have
this
been
is
removed
something.
twice, sir.
yes, sir. I have also been
Yeah,
removed twice.
so who is doing
Okay.
this?
The answer is there in the meeting.
Yes, I'm here. So I don't
So sir,
understand who is
some
doing.
problem is going on. So what
Yeah,
to do?
so I can make you the presenter, but then like it will send an invitation to you, and you have to accept that.
Okay. This is hold on. Sir, where I will get the notification?
Wait a second. You will get it in the. You'll get it in your email. Just a second. I'll tell you.
Sir, we can change the roles in the participant list.
Yeah. I'm going there and trying to do that. I'm trying to exactly do that. But I'm not finding Arijit in the list. That is the issue. Okay, I found him. All of you, please mute yourself. Yes, Arijit, I have made you a presenter.
Okay.
Everybody else is an attendee.
Okay. Yes. Okay, so can you see my screen?
You can
Hello.
continue, Arijit.
Okay, so actually I don't know from where I need to continue because I think I'm muted. So
No, I think you can start with the DFS part.
okay. So I'm starting from here only. Okay, so basically this is the thing. So we'll start with the BFS part. So as you know that to do the BFS we need to use the queue. So here is the thing. So here our initial start state is 02 as we are here. So basically we means the frog here in the 0.1. So basically we just enqueue that thing into the queue. Okay, so can you please mute because it's loud. Okay, so 02 in the queue. Now the thing is that the next step is that we need to dequeue the front element from the queue and need to add its adjacent neighbor to the queue. Basically, this is the thing. So we just dequeue 02 and add its adjacent 01 and 03 to the queue. Now we can say that you can also say that why we are not adding 1 because 1 2 is also the adjacent. But the problem with the 1 2 is that 1 2 is unstable, and so we are not want to go to an unstable node. So that's why we are just interested with the other is 0 1 and 0 3. Now, what is the next step? So, okay, again we are NQ the 0 1 and 0 3. That is fine, but we need to mark the node also, because like after some time it may be possible that we are again want to go into this node and we will be create some kind of want to mark this 0 1 0 3. So basically it will be this marking 0 1 and 0 3. And that these two are already explored, and those two are already the. So what will be the next step? Step will be that we need to DQ the front element. Basically 0 1 is the front element, 0 1, and we need to like its neighbor. Now 0 1 is has 0 0 and 1 1, but we are not going to 0 0 because it is unstable node, and we are also not going to 0 2 because 0 2 is already visited. So just one option left. So it is 1 1. So we are just NQ 1.
Sir,
And we
your
are
voice
just
is not clear at all.
Which one?
Yes, sir, your voice was like, there is a lot of resound in your.
Is it from my side or someone is like unmuted and?
Sir, now it's fine, sir. Now it's fine.
Yes, sir, now it's fine.
Yes.
So, okay, this up to this mark, is it okay, or so I again need to tell?
No, sir, it's okay, sir.
So, so this is the state we already covered 0 2, 0 1, and 0 3. From them 0 2 is already DQ, so there are only two elements left in the queue, so which is 0 1 and 0 3. Now what will be our next step? We want to DQ the front element, which is 0 1, and NQ its adjacent node. So what will be the adjacent node of 0 1? So this is the 0 0, 1 1, and 0 2. Now among these three, 0 2 is already visited, so we don't want to NQ this. 0 0 is an unstable node, so we don't want to NQ. So only option left is 1 1. So we just want to add this 1 1. So here you can see, like we just DQ 0 1 and added 1 1 to the list. And again, one thing you also need to do is that we need to mark this node. So that is 1 1 is also visited. So this is the state now. So now it will continue again what will be the front element of the queue? 0 1. Okay, so we want to DQ 0 1. We want to DQ 0 1 and we want to add its adjacent. So its adjacents are 0 2, 0 4, and 1 3. Now among these three, 0 4 is unstable node, so we don't want to add. 0 2 is already visited, so we don't want to add. So only options left is 1 3. Okay, so we are adding 1 3 at the back of the queue. Okay, and also we are marking this thing 1 3. So now this is the state of the queue. Now what will be the next element we want to DQ? So which is the front element? See, it is the 1 1. So this is the 1 1 element we want to DQ. Okay. Now for 1 1 there are two options. So there are three options: 0 1 0, 2 1, and 1 2. And okay, so 1 1 has four options: 0 1. So you can go any one of the direction from 1 1. But among these four options, 0 1 is already visited, 1 2 is unstable node. So we have just only two options left: 1 0 and 2 1. Okay, so we are adding 1 0 and 2 1, and also mark this thing. So it is now it will go on. So again you will remove the front of the queue 1 3, and again DQ 1 3, and you will add this neighbor. So basically it is 1 4 and 2 3. So we are adding 1 4 and 2 3, and also marking these two things. Okay, now this is the state. Now we want to DQ the front of the queue, so that is 1 0. But the thing is that from 1 0 you don't need to you are now you have no options left now. So because all the nodes are visited, like 1 1 is visited, 2 0 is unstable, 0 0 is also unstable. So you don't have any options. You just DQ 1 0. you just DQ10 and you don't have any reachable neighbor from 10, so you don't need to add any node to the queue. So basically now this is the state. Again now 21 is the front of the queue. Again you want to DQ21 and you need to add its reachable neighbor. So what are the reachable neighbor from 21? It is only 31 because the east and west part is already unstable, so you don't want to go into that direction. You only have the one option left, which is 31. So we are adding 31 to the queue. Okay. And you are also marking this thing, so that is fine. So we are just fast forwarding all these things, so the same thing are going on and all. Okay. Okay. So again, this is the now the queue situations is 3-1. So now we have two options, 3-0 and 3-2. So we are adding 3-0 and 3-2 to the queue and also marking this as green, so it is already visited. Now we are removing the front of the queue, so which is 3-0, but 3-0 don't have any reachable neighbor, so we don't need to add anything. Now this is the thing. Now from 3-2 you can go to 4-2. Okay, so you are removing 3-2 and you are adding 4-2 to the queue and you are coloring it. Okay, this is the color. Now again same thing, from 4-2 we have only one option, that is for 4-3, because 4-1 is unstable, 5-2 is unstable, 3-2 is already visited, so only option left is 4-3. So that is 4-3. So you are adding 4-3 to the queue, and this is the picture. Okay. So from 4-3 there is only one option left, that is 5-3, because all other options are already somehow maybe visited or maybe these things are what happened? Hello.
Yes, sir. You are.
Yes, sir, you're audible, sir.
I am audible, but again, my presentation.
Yes, sir, it's visible, sir. Everything is visible.
Is it visible? Okay, yeah.
Yes,
Yes, sir.
Yes, sir.
So you are into it. So you are like, there is no issue till now, no? So now from 5-3, so only one option is left, because 5-2 is unstable, 4-3 is unstable, and 5-4 is only the node you can go. So you are just in DQ 5-3 and add 5-4. Now you are already reached your goal state. So you don't need to do anything. So you are already reached the target state, and you can just print, okay, so the path is present from 02 to 54. You don't need to the print the path. So maybe so it does not matter in which way you follow and reach 54. You just, so if at the end of the operation, so in the process, if you find your your target state in the queue, front of the queue or any like in the queue, you can say that like that the target state is can be reachable from the start state. So this is the BFS part. So is it okay? So is there any questions from the BFS part?
Sir, with this method, sir, is it possible to also print the path sequentially?
Yeah, it can be possible, but for that you need to maintain another queue, and you need to just write the parent of each of the positions. So for 5-4, you need to what is the parent of 5-4? Like parent means from which node you came to 5, actually 5-3. For 5-3, you need to say 4-3. Okay, so there is another extra complexity needed. So you need to add another extra array to maintain those information, and you then you need to then backtrack. You need to add some extra point also, but that is the whole thing. So you need to add you need to make another extra queue or another data like array to save the parent structure, so that you can backtrack. Okay, this is the BFS part. And in the last year question for the BFS implementation, they do not ask for this part. So they just ask for, is it reachable or not? So if it is reachable, you just print it is reachable, and if it's not, then you will not print it. It's not. Now another thing is that like if the insect was in suppose was in 50, then you cannot reach 50 any like from 0 to, there is no way to reach 50. So after like at the end of your like BFS operation, you will never add 50 to your queue. So you can say that like the state is not reachable. Sometimes
Means like after at the end of my
yeah,
operations, we just
you can
reach the
ask
queue.
when your code will end. So what is the stopping criteria of this algorithm? Can you tell me? So from this whole step, what is the stopping criteria?
When there is no neighbor.
When there is no neighbor that can be added
There is
to
no
the queue.
neighbor, that is fine, but there is no element in the queue.
Yes, sir.
Sir, if it is when there is no element that was not registered, it was different case now.
No, no. Suppose like you can take this example. So suppose 50 is your target state. So you will see, you will encounter such a point when you can see that there is no element in the queue, like there is no element in the queue, and you have not reached, like you have not discovered 50. Okay. Because like this is the terminating condition until the queue is not empty, like you will do this thing, and if in that step in that like in the middle of the somewhere you will find those like target state into the queue, you will say that the target state reached. If not, then it is fine. So you can try it, like you can take this example and take 50 as a target state and do it, like you can check. So when you need to stop, you will understand. So basically this is the thing. So when there is no element in the queue and you also not reach your target state, so both conditions should be met. So anyhow there will be a time when there will be no element in the queue. If you properly color your node, so if you just not go on the loop forever, you will like come into a point where there will be no element in the queue. So that is fine. But the thing you need to track is that the target state will not like in the any throughout the algorithm there will be like the target state should not be into the queue. So then you can say that like target state is not. So just take this take this example and just change the 54 to 50 and see. That is easy. That is not okay. So we'll go to the next part with DFS. So for DFS, so what will you use, stack or queue?
Stack. DFS we need to use stack.
Okay, so now, but the one thing you need to remember here we just need we don't need to tell that, like not only need to tell that is the path exists or not, but we also need to print the path. Okay, so the DFS step is more involved. So just some minor modification. That's all. So okay, so we are just pushing your first initial state, that is 02 into the stack. So this is the stack 02. And then you just go on. So in the DFS you can go anyway. So you can go to the 01 or 03, okay, or 012. But 12 is an unstable node, so we are not going to that. But we are just like randomly we are like we can go to 03. You can ask, so why I'm not going to 01? Just maybe we are just having heuristic, so we will always go to the right side or something. That's not an issue. So okay, so we will go to the 003. Okay, then we are pushing. So basically, so now 03 in the top of the stack. Okay. So we also we are coloring 03. Okay. Again, from 03 you can go to 113 or 04, but 04 is already unstable, so we are not going to that. So we are pushing 03 into the stack. So basically this is the state, and from 13 you can go 14. or 2 3, but just for the sake for this problem we are just thinking to push 1 4. Okay, so we are pushing 1 4, and okay, so this is the step. Now if you see from 1 4 there is no other options to go, like you cannot go 1 3, you cannot go 1 5, 2 4 or 0 4, so you need to backtrack. So you need to DQ 1 4. So there is no unexplored neighbor for 1 4. So you just need to pop 1 4. Okay. So we are just popping 1 4. Okay. So this is the after the popping 1 4, that is the stack. So now what is that the top element of the stack? This 1 3. So this is the 1 3. Now from 1 3 you can go to 2 3. Okay. So from 1 3 we are going to 2 3 and we are marking 2 3. Now from the same thing happened for from 2 3 there are no options, like we cannot go to 2 2, we cannot go to 3 3, we cannot go to 2 4. So just we need to backtrack to our parent, which is 1 3. So we just pop. Okay, so basically for like this is the same step going on, so I'm just writing all. So we are going to we are just popping 1 2 3. So 2 3, after 2 3 we are going to 1 3, but from 1 3 there are no unexplored neighbors, so we are popping 1 3, and from 1 3 we are going to 0 3. From 0 3 also there are no unexplored neighbors, so we are popping 0 3. So basically, so I'm just fast forwarding those things, so these steps are like sequential one by one, but like for simplicity I'm just popping three element one by one. So after that, just we have just one element left, so 0 2. Now from 0 2 we will go to 0 1, because there are no other options left, because 1 2 is not like this is unstable. 0 3 is already visited, so only one option left, so that is 0 1. Again, so for simplicity we just add all these things together. So basically from 0 1 you can go to 1 1, you can go to 2 1, you can go to 3 1. So basically just take it single step, but for there'll be different steps. So this is the step. Now from 3 1 you can go to 3 0 or 3 2. Suppose we are planning to go 3 0. So 3 0 we just mark it. We just mark it 3 0. But the problem is that from 3 0 there is no way to go. So we need to backtrack. So we are just popping 3 0. We are just popping 3 0, and this is the stack now 3 1. Now 3 1 we can go to 4 3 2. Okay. Now again, from the simplicity, we're just merging multiple steps to one. So from 3 1 we can go to 3 2. From 3 2 we can go to 4 2. From 4 2 we can go to 4 3. From 4 3 we can go to 5 3. And from 5 3 we can go to 5 4, because there are no other options. So just merge all these steps together. Okay. So this is the stack now. Now the point is that like the top of the stack is your final state, the target state. Okay. So okay, so now the target state as in the stack, so you can say that like this state is like reachable from your start state. But the point is that how will print the path. So what will be your way to print it? So can you tell me what is the way to print the stack, like print the path from target state?
So we'll just take an array along with the recursion. So every
So
time
we'll just we'll implement the stack
using
using.
elements.
Sir, we need to reverse the stack to get the original path.
Yeah, because that we don't need to do anything. Just pop the stack, and that will be the your result. Just you can see this is our stack. We just pop 5 4. Okay, so that is the
Sir,
last
but
step.
we have to store them, no, sir? Like
What?
we have to print it in a reverse manner from 0
Okay,
to 2.
no, okay. If you want to, like I'm just saying, so if you want to print the reverse order from start to from the start to last, then you will just need to reverse. If you just that is the thing. So I'm just saying this thing. So that is fine. So that is a implementation thing. So that is just saying that you just you don't need to do anything fancy. You just pop this stack and just print it. That is fine.
Sir, here the stopping criteria will be either the last element entered is equal to the target element, or there is the stack is empty.
Yeah, absolutely. Same thing as PFS, but here you need to print the stack, so that's why you just pop every element, and so you can see that from 5, 4, 5, 3, all these things are marked. At the end, you will. So these things is clear, no? Any questions about this?
Right? We can start from 5, 4 and go to 0, 2.
Yeah.
In the sense. We start our BFS or DFS from 5, 4 and then we end up at 0, 2. So that is another way of doing this, right?
Yeah, same thing. Same
So
thing, but
that
the thing is that, like,
print.
yeah, if you this is the same concept. If you can see you, like I can see you, then you can see me. Same thing. So there is no other way, because it is not directed and something like that. So you can see this is a bi-directional. So if you can go one state to other, that state can also come to you. So that is fine. Okay, so I think it is okay. So I'll go to the next. Okay, so some extra point for this thing. So last year they also mentioned some templates of queue and stack. So basically you just you just write your code adhering this template. So basically you just need to define the point structure with x and y, both two coordinate. You just want to add the queue structure like this, and you just implement all these things. So empty, enqueue, dequeue. I think you already have done this in this year also, like previous assignment, or I think last assignment. You are implementing the stack and queue. So the same thing. You just use those things. You don't need to, like, you are not bounded to use any STL. So you need to write your own function for DQ, NQ, you know. Same thing goes for stack also. You need to write your own function for push, pop, and all this. Okay.
So here we need to push then 2 points, right? The x coordinate and the y coordinate together.
Okay, so that's why you are just defining one structure with point. So you are just pushing points. So you are not individually pushing x or y. You are just like bundle this x and y into a structure called point. So you are just okay. So can I like go on to the next topic? I think it is. Okay, so the next topic is So next topic is not cycle detection. It is like strongly connected component, but I don't have any PPT, so that's why I'm just will draw it on the. Okay, I think it is visible, so I'm just lighting it. Okay.
Yes, sir.
So just taking the same example from GitHub and Git, so that it will be easier if you want to follow. If you want to perform this. Okay. Okay. So this is a directed graph. Now the thing is that what is SCC? So strongly connected component. So have you heard that about previously? What is strongly connected component? So a strongly connected component in a directed graph is that. So you can think of this part. Okay. Okay. If you see this component, you can go from any vertex to any vertex. So basically, this is a cycle. So you can go from 1 to 0, 0 to 2. So every node is reachable from everywhere. So this is a connected, strongly connected component of this path. Okay. But we cannot say for the whole graph, because like you can go from 0 to 3, but you cannot go back. Okay, from 3 to 0. Same thing, you can go from 3 to 4, but you cannot go back. So this is another component, and this is another component. So this graph is three strongly connected component. One is 0, 1, 2. Another is just 3, and another is just 4. Okay. So this is the thing. So now the question is that, like, if like you are given the if you like, suppose we are giving you a graph and ask you to give me what are the different component, like what are the different strongly connected component in the graph. So how will you do that?
Sir, first of all, I will check the number of cycles in the graph.
Yeah, but how? How will you check? So suppose take this example and tell me how will you check number of cycle in the graph.
Sir, initially I assign them color white, and after that I will go on traversing and looking that which node is adjacent to it, and assigning it to color gray. And if color gray
No, that
is
is fine. That is, you are saying the like cycle detection algorithm. That is fine. I know cycle detection. The thing is that, like, how will you use this thing to do this thing? So is it possible to do this thing? So suppose you are finding the cycle 1002 and this cycle you will find. So that is fine. So how will you discover that 3 and 4 are also there? So is it possible to do this one? So you are saying that you will iteratively use cycle detection algorithm throughout the graph. That is the thing, no?
yes, sir.
Okay. So I need to check, is it possible? But I do. There are some issues here and there, I think. So, but the thing is that you can solve this problem with DFS. So DFS will help you to do that, because you can, like, ultimately you will need to find the cycle. So with DFS you will find the cycle also, and there are some other properties that will help you to do that. Okay, so just take this. I'm just again drawing this thing. So I'm just doing. I will do the DFS for this. This is one. Okay. And this is 2. This is 0. Okay, so the thing is that, like, if you see this graph and suppose you are starting a DFS, so can you see me what is the the order by which DFS will go? And another thing, okay, so just think of this thing. So one thing, what we will do is that we will do the DFS, that is fine, but another thing we need to do is that we will, like, suppose this is a graph, okay, this A, B, C, okay, and we will do the DFS. So basically A will call B, B will call C, okay. Now the thing is that, like, we will add A to the stack when B is finished. We'll add B to the stack when C is finished. So something like that. So we'll call A, we'll go to the B, we'll call, like, this is the pseudocode DFS. We'll call DFS, say we'll call DFS B, okay. DFS B will call DFS C. But from DFS C we'll have no options to go, so we just put it into the stack, and we'll go back to B. and in the B there are no other options, so we'll go back to B. Yeah, we'll put the B into the stack, and again we'll go to the A, and there from A there is no option, so we'll put the A. So if you see this kind of ordering, so A, B, C, you can see. So what is noticeable from here is that, like, if like A, like B is a, like, suppose A is a portion and B another portion, and we can go from A to B. So it is always in the stack, so that B will be finished at last, like after B finish. So the finish time with B is always less than finish time of B. So finish time of A is always greater than of finish time of B. Same thing, finish time of C. Okay, so that is the property of DFS. So DFS always, like, if you follow the stack structure, so either if you follow the function call, so A calling B, B calling C, so C calling D or something like that. So we always finish, like, D will be always finished first. After the D is finished, then we will go to C. After C is finished, then we will go to B, and after B is finished, we will go to A. So the finish time will A is always higher than B, then C, then D. So that is the. So you'll also need to check this kind of thing here. Okay. So for this thing, so suppose we are starting from 0. Okay. From 0, we are starting from 0. Now what we can do? So we are calling, we are going 2. Okay, so this is from 0 is calling 2 DFS. Okay, we are calling 0 DFS. From DFS 2, there is only one option, we are going to 1. Okay, but from 1 there are no other options, so we are just backtrack. So before backtracking from A, we are pushing A onto the stack. Okay, so we are now into the 2, and from 2 there are no other options. So before backtracking from 2, we are just pushing 2 into the stack. Okay. Now from 0, there are another option. We can go to 3. From 3, we can go to 4. Okay. But 4, there are no other options. So we are backtrack from 4, and before backtrack, we just add to the key. And from 3, there are no other options. So we are backtrack from 3 and push 3 into the. And at last, there are no other things. So we are just backtrack from 0. So this is the ordering. Okay. Now, if you see this ordering, you can see a significant characteristics of DFS. So the finish time of 0 is always higher from finish time of 3 and finish time of 4. Okay. Finish time of 0 is always higher from finish time of 3 and finish, that is also higher than finish time of 4. And what is 3 and 4? 3 is another component, 4 is another component, and 0 is a like member of a component which is connecting to the other connected component. So 0 is member of this strongly connected component. So suppose this is SCC1, this is SCC2, strongly connected component 2, this is SCC3. Now you can see that, like, the connected component of SCC1 to SCC2, which is 0, is like finishing higher than the SCC2. And same thing from SCC2 to SCC4, there is a path, and this is the connected component from, like, there is a this member from the SCC2. This is the connected member of SCC2, and this is the connected, like, connecting to the SCC3. And so the finishing time of 3 is higher than the finishing time of 4. So are you getting this thing? So this is the,
can it be like the finishing time of A is greater than equal to the finishing time of B, because Like you can think of an example when another node is actually connected to 2.
Okay,
So,
just hold on, just tell me the graph, then we can do it.
so
Tell
just
me
the
the
previous
graph.
we will just add another node at 2.
Okay, so basically you are saying 1, this is 2 already there. So this is 0. Okay. Okay, and tell me what thing we need to add.
Another node 5 at 2.
It is outgoing or ingoing?
So outgoing.
5.
Yes, sir. So in this case,
Okay.
What with the stack structure?
Okay, same thing. Suppose now tell me what are the different component from here. This is one component. This is one component. This is one component. This is one component. Okay.
Yes, sir.
Now do the DFS. Suppose we are doing the same thing. We are starting from like this is our DF. This is our stack. Okay. So we are starting from 0. We are calling 2. Okay. Okay. We are calling 2, and from 2 we are calling 5. Okay. That is possible. No issue. But from 5 there are no other options. So we are backtrack to 2, and we are putting 5 here. From 2 there are another option. We can go to 1. Okay. But from 1 there are no other options. So we are backtrack from 1 to okay, yeah, we are backtrack from 1 to 2, and from 2 there are no other options. So we are backtrack from 2 to 0 and putting 2 into the stack. Okay. Again from 0 to we can go to 3, and 3 we can go to 4, but 4 there are no other options. So we are just putting 4 here, get back to 3, and from 3 there are no other options. So we are putting 3 and then get back to 0, and from 0 there are no other options. So we are out of that. So this is the stack. Is it? Okay. Now see, the same property is followed here also. So suppose I just yeah, putting this is the name. So SCC, this is SCC1, this is SCC2, this is SCC maybe 4, this is SCC3. Now what is the property that I'm saying? That if like this, take this thing as you are saying. So SCC1 we can go to SCC2. So what is the connected component, like what is the member which is connected from SCC1 to SCC2? It is 2. Okay. So in the DFS tree you will see the finish time of 2 is always greater than the finish time of 5. Is not it?
Yes, sir.
So now is it clear or not?
Yes, sir. I was just telling that, sir, in this case, the finishing time of 1 and 5 are same because they have no other node and they have
there is no, like, we cannot do any distinction with 1 and 5, because the only concern is that the terminal node of one component to the other. So for SCC1, so SCC, like the strongly connected component 1 is maintaining its communication with other component through 0 and through 2. So these 2 is our point of contact. So we are not bothering about 1.
That means just, sir, it is a parent-child relationship that we are following here.
Yeah, you can say so. So basically, it is a now 5 is a sync. It is like following in this way. So basically, you just need to remember this property. So the strongly connected component of one like the member of one strongly connected component which is connecting to the other strongly connected component is always finished later after that thing. So just for this example, so SCC1 is connecting with SCC3 via 0. So in the DFS, 0 will always finish first, later than 3. Same thing will follow here also. So this thing, this is the important thing. Okay. After, so now with this thing, so what we have already got is that, like, we have pinpointed 3 in the DFS that we have got get. So here you can see, like, always the strongly connected, different strongly connected component. This is the strongly connected component connecting of 1. This is the strongly connected component of 3. This is the strongly connected component of 4. And this is the strongly connected component of 2. You can see the way they are like if you draw the picture, it is like this way, no? If you see, SCC1 is connected to SCC3, SCC3 is connected to SCC4, this is SCC4, and SCC1 is again connected to SCC2. And if you see the DFS, you will see the order also. So as per the DFS, one should be higher, like the connected component of 1 should be higher, like finishing time of this should be higher than SCC2. It is maintaining this property. 5 is below of 2 because this thing. Same thing from SCC1 for SCC3 is this thing. So 0 is up, then 3. Same thing. 3 4 is also same. So after doing the first DFS, we are pinpointing the communicating node between this connected component. So we are just pointing. Okay, we are just marking. So what are our finding? Our finding is 0, 2, 5, 3, and 4. So why you are seeing this is our finding? Because these are the important nodes. These are the boundary. So we need to track in our next stage. So can you see what will be the next stage? So any idea or anything? Are you getting or just hello?
Sir, can you repeat that part? What you asked the question?
My question is that we already done the DFS. That is the first step. We just identified the different connecting points of one strongly connected component that is connecting to the other strongly connected component with DFS. So okay. So why we are doing the DFS? In the first place, we are doing the DFS. What we have achieved till now after doing the DFS till first part. So can you tell me what is the thing we are understanding? Why we are doing the DFS here? So okay, just take this graph and while doing the DFS, what we have got, we have just 0 to calling 2, 2 to calling 1, and 1 there is no option, so we are backtracking. So this is the thing. So 2 there is no option, we are again backtracking. We are going to 0, 0 2 we are calling 3, we are calling 4, 4 is there is no option, backtracking, again backtracking. So this is the.
Sir, 4 will be above 0 and 3 now. Means 0 will be above 3 and 4.
Okay, so this is mistaken. So I just this. Now is it okay?
Yes, sir.
Sir, could you please do it fast? The class is already half an hour late.
So
It is
like
already half an hour overtime. Can you do a bit faster?
okay, so I
So,
can.
Urijit, I think we should be closing now.
Okay.
So,
Okay.
is it done? Is the ACC done? The idea? The main
The
idea?
idea is done, but there is another step to get the answer. So it's the first step, and then there is another step to do.
Okay.
So the thing is that the thing is that we can take like if there is
maybe
another
you should finish in another 4 or 5 minutes max, because they have to go for lunch and then again come back for their classes.
like
It's
is it
already very
possible
long.
to do it in the weekend for another half an hour? Then we can wrap it in the
Yeah,
like,
I think that is better.
because there is no point to cruising through this thing, so there will be no understanding on
Yeah,
this.
they will. Yeah, I think that is a better way. So students, like over this weekend, like if we schedule a half an hour to 40 minutes extra class, would that be fine with all of you?
So we already have a class tomorrow from 4.
That's fine. Like it's some, it will be some hour where like you don't have any classes.
Sir, we can finish right now. Actually, we don't have any class from 2.
Okay.
Like you can briefly explain what to do, and we will try on our own once.
Yeah, because somebody complained about the stretching of the class, so that's why we were thinking. So, okay, Orijit, I think you can wrap it up in another 10 minutes maybe and finish it up.
Okay.
Sir, but like many of them have left.
Yes, sir. So extra class would work good, sir.
Okay,
So more than half of the people have left.
Yeah. So let us do one thing. Let us have an extra class. Okay, so we can quit today, and since this will take some time, let us not hurry, and the concepts are interesting as well as important. So let us meet back again. So we will try to have a convenient timing for both students and the tutors, and then we will see what can be done. Okay, so let us do it in a little more slower pace. So probably over the weekend we will ask for a slot, and accordingly, like, we can proceed. So it's fine to go a little slower, not a problem. So Orijit, we will coordinate this with the students, and then we can arrange something. Say maybe on Sunday, somewhere around 5 p.m. or 5:30 p.m. in the evening or something like that. We will try to coordinate.
Okay, sir.
Okay, so let us close it here today. Okay. Thank you guys for staying back.